We're going to build on what we knew from the previous notes and about sublevels, about energy levels, sublevels, and number of electrons. And we're going to try to wrap it all nice and neat into a more convenient thing called an electron configuration. So an electron configuration is the arrangement of electrons in an atom. Is the electron configuration. So it's showing you how many electrons there are and where they exist. Okay. Now normally we will show them in the ground state right here, but you could show an excited state one as well. So the easiest way to follow these is to use the Alfval diagram like we have here. So this is essentially what I drew in the previous video, but a little bit neater. And you can fill in your electrons here. Now, notice that you must follow the Aufbau principle, which means that you must build from the lowest energy first. So the first sublevel that's going to happen is going to be 1s, and then 2s, and then 2p, and then 3s, 3p, and then we're going to go straight into 4s, and then we're going to go into 3d, and then we're going to go into 4p. There will be questions about that. Now, all of this stuff above the line here is not tested because it really depends on the atom. Once you get to things higher than this level, they start getting so close together it's hard to tell. So just know that we go from 3p to 4s to 3d to 4p. If you tattoo that on your forehead if you need to. Now remember, Hund's rule was the one where you had to have an up arrow, up arrow, up arrow, and then down, down, down. You couldn't do an up, down, up, down, up, down. You cannot do that. So an example of what not to do would be if you had 3p right here. If you did this like that, that is not correct. Okay? You would want to write, if you were writing 3 electrons in 3p, you would want to write an up, up, up. Okay? So this one is correct. This is not correct. Now the Powell exclusion principle is hard to not to follow in here. You just can't put more than one electron in the same place. Now there are 2 exceptions to the Aufbau principle, and that is going to be chromium and copper. So there's a reason for this. So chromium, I will draw its just orbital diagram. So what we're going to do is we're going to show the 4s and we're going to show the 3d, and we're just going to skip all the stuff in between. So I'm going to show for chromium, it has the 4s and it has the 3d. 1, 2, 3, 4. Oops. 5. Okay. That's the 3d. Now normally what you would like to see is you would like to see this. You would fill up 2 electrons here and you would get 1, 2, 3, 4 for chromium. Now for, that's a little confusing. But this is not what happens. It's not what happens. What you actually see is you see this. S, 3d. You will see this 1 electron go from here and get promoted to the 3d, okay, because it's actually more stable. So it's more stable to have all of them half filled than to have this one totally filled and then this one blank. Okay, so this one is preferred. This one is correct. And now copper is the same reason. It is going to be like this. I won't show the non-example. I'll just show you it's with 4s, and then we have 3d, 2, 3, 4. This is 3d, and so it will have an up arrow here, up, 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 and then down, 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 like that. Okay, so those are the two exceptions that you have, and exceptions like to show up on the test. So fill an Aufbau diagram for nickel, right here. So for nickel, nickel is the atomic number is 28. So that must mean that I must need to place 28 electrons. Ooh, 28 electrons. So I'm going to place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Boom. 28. So we would have 2 unfilled, 2 half filled, and then 3 totally filled. And then for bromine, we need 35 electrons. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Excellent. So there are easy ways to write this way. We can, instead of drawing all of this junk and getting all that down there, we can really just abbreviate this stuff. So watch me do this. This is your first electron configuration. We'll take 1s, and since we'll say that's 1s, there are 2 electrons here, so I'm going to say 1s, 2. Then I'm going to say 2s, 2. And then there are 2p. How many are there? There are 6. I'm going to say 3s, 2. I'm going to say 3p. There are 6. Then I'm going to say 4s, right? Because you have to go from p to 4s. So I'm going to say 4s, 2. And then I'll say, go to 3d, 3d. There are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons. So that is the electron configuration for nickel. Electron configuration for bromine is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p5. So the superscript here is showing you the number of electrons, and then this is showing you the energy level. This is showing you the sublevel. And so really the only valence electrons are the ones on the end right here. So these are the valence electrons. Okay? The highest energy level. Okie dokie. You don't have to point out the valence electrons. Sorry. So there's an easy way to see that on the periodic table. There is a pattern. We all know that these are, this is energy level 1, this is energy level 2, this is energy level 3, 4, energy level 5, energy level 6, and energy level 7. So pop quiz, guys, what is this one? Well, this one should be right here. So it's actually energy level 6, and this is energy level 7. So this is this whole area. I'll do this one in blue. The S block. Don't forget, helium is actually supposed to be over there. Now this whole area is the P block. And this whole area right here, this is the D block. And this area, this guy down at the bottom, is the F block. So all of our F electrons are down here. You really don't have to know much about it. You just need to know that the F block is down there. So here in this row, this would be 1s. And just remember helium. We're going to draw an imaginary helium right here. Here's hydrogen. This would be 2s. This would be 3s, 4s, 5s, 6s, 7s. And then for P, this is the second row. So this would be 2p, 3p, 4p, 5p, 6p. And now, remember, we went from 4s into 3d, right? So for the D block, even though this is the fourth row, we're going to do n minus 1 here, and we're going to say that n minus 1, and that's going to be 3d. 4d, 5d, 6d. And then when we get to the F block, this is going to be along the same lines. It's not going to be n minus 1 though, it's going to be n minus 2. So this is the sixth row right here, but this is going to be 4f, it's going to be 5f. Okay? So all this is really showing you is what is the last term on that electron configuration. So we'll go back to our nickel example. Nickel is located, that's zinc, that's copper, and so this is nickel. Nickel is located right here, so its last one is 3D, right? Yep, you see that? And it is 1, 2, 3, 4, 5, 6, 7, 8 over. So its last configuration was 3D8. So you can easily find their electron configurations just by looking at the periodic table. It's like they planned it that way. And for bromine, bromine is right here on the same row, but it's over here. So its last configuration would be 4p, 1, 2, 3, 4, 5 over. So 5, 4p, 5. See how that works? Aha! Very good. It's like we planned it that way. This is very important. Very good. Building blocks of chemistry. So using the periodic table, let's write the electron configurations for the following elements. So let's do oxygen. Oxygen has 8 electrons, and where you see it on the periodic table, it's right there. So that is in the P block, and it is 1, 2, 3, 4 over. So its last configuration is going to be 2p4. So we're going to start with 1s2, 2s2, and it's going to be 2p4. Okay, it's really handy to have a calculator here. And then for magnesium, we're going to start again. Here's magnesium. We're going to start at hydrogen, and it says 1s2. Don't forget to include helium. It's going to be 2s2, 2p6, 3s2. See how that works? 1s2, 2s2, 2p6, 3s2. Iron is here. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4s2, and now 3d, 1, 2, 3, 4, 5, 6, 3d6. For antimony, now we're starting to get mean because they are really long now. So now we're in the 5th row, and it is going to be the P block and 3 over. So that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 5p3. Okay, you'll notice that it never changes. The sequence never changes. It's just where you stop is what changes. Now europium is in the F block. I'm not going to be that mean. I'm going to take that out. So yeah, so you can see they get really long. Let's write a shorthand configuration. So what you can do here is you can go back to the previous noble gas, and you can that will represent what it is. So the next one is carbon. We have carbon here. So we're going to back up. We're going to back, beep, 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 and we're going to back up all the way to the previous noble gas, which is helium. Okay, so we're going to write down helium in brackets. And then we're going to start from there. We're going to start from there, and we're going to start counting up. We're going to count up 1, 2, 3, 4. So that's going to be 2s2, and then 2p2. For calcium, we're going to go to its previous noble gas. So here's calcium right there. We're going to go to back up to argon. So I'm going to write argon in brackets, and that symbolizes all noble gas configurations up to argon. And so now I can just move on back to argon and up to potassium. So this is going to be 4s2, and that's going to be 4s2. That's it. And then bromine, I'm going to type right in argon again. It's going to be 4s2, 3d10, 4p5. And then xenon. Ooh, xenon is a noble gas. So can you just write xenon right here? Oh, sorry. So can you just write xenon? Nope. That would be too easy. You can write krypton, the noble gas before it, and then you start taking, this is going to be 5s2, and then 4d10, and then 5p6. And we won't do thorium. That's too mean. Now, we're going to write the Lewis dot symbols here, and this is super easy. All you have to do is write the valence electrons here. So for sodium, hey, guess what? Sodium has 1 valence electron. That's because its last configuration is 3s1. So the number of valence electrons is how many s and p electrons it has. So it only has 1 valence electron. So we're going to write Na with a dot right here. That's its Lewis structure. Phosphorus, its valence electron 1, 2, 3, 4, 5. It's going to have 5 valence electrons because it has 5 over. So it's going to have 1, 2, 3, 4, 5. For iron, here's a thing. Iron, it actually only has 2. It's a transition metal, don't do iron. And then bismuth, don't do bismuth, but argon is a noble gas, so it looks like this. We'll do a lot more on Lewis dot structures later. But I want you all to have a great day. That actually concludes all of the notes. Take care. Sorry the video was so long.